So following on from the previous two videos, let rho be the limit of the ratio of the two. So in your mind, try to picture this in your mind. Try to picture this in your mind. So this is your an plus 1 over an. Now an plus 1 over an is not the same as the original sequence. We are not looking at the original sequence. We are looking at the ratio of the two. So try to picture this in your mind. Don't picture this. Don't picture the original sequence. Okay. So for the limit of the ratio to exist, it will mean that this thing here is heading towards a limit rho. And what that means, remember, definition of limit is that there exists a capital N where all n beyond capital N for any given tolerance epsilon here, and then you've got your epsilon here. So this is rho plus epsilon, and then you've got your rho minus epsilon. So for the limit of this thing to exist, rho, then try and picture this in your mind. For all n beyond capital N, it must fall within this band plus epsilon minus epsilon. It must fall within this band here. That's a true definition of limits. So try to picture this in your mind. So when you read this statement, try to picture this in your mind. Okay, and then because we are addressing for rho to be less than 1. So remember, it could be rho could be equal to 1. It could be bigger than 1. It could be smaller than 1. We are now addressing the case where it's smaller than 1. So we are going to forget about this. We are looking at the case for rho being less than 1. So hang on. So now if you look at this, so we are looking at the case where rho is less than, so this is 0, this is 1. We are looking at the case where rho is less than 1. Now rho is less than 1. We are going to now hang on, let me think. We are now going to introduce this r here. We are now going to introduce this r. So you've got your limits. Well, so hang on. So for you to have a limit of rho being less than 1. So this is 0, 1. So rho is going to be less than 1. Now define this r. Define this r to be somewhere in between rho and 1. So let r be, I don't know, anywhere in between the two. Because suppose your limit, suppose your limit is 0.9995, say. So you can see that rho here is less than 1. So let's go down here. So let's just imagine rho here to be 0.9995. You can always select an r where it's always between 1 and rho. So you can always select r to be 0.9996, say, and then this r here is always between rho and 1. The point here is that remember, this here is saying the limit of the ratio of the two converges to rho. So hang on. So what that means is this. Bear with me. You've got your rho here, and then you've got your ratio of the two here. So it's heading towards some sort of limit. So hang on. So don't forget, this is your an plus 1 over an, and then we're saying, remember, for limit to exist, there's a plus epsilon, there's a minus epsilon. So it must fall within that band. Remember that capital N, all n beyond capital N, it must fall within this band here. Plus epsilon, minus epsilon. The point here is that let's this thing here be r. So let this thing here be odd. The point is that if you read this statement, it's saying the ratio of the two must always be less than less than r here. So it must always be less than r, because beyond, for all n, beyond capital N, it must be within this band. So you can definitely say that r is always greater than the ratio of the two, because remember this line here represents a ratio of the two. So beyond capital N, then you can definitely be sure that it's going to be less than r. Okay, so we are now at this stage here. I will continue in the next video. But for sure, let's say this is 0, 1, and then this is your limit rho here, and then there must exist a capital N where anything beyond capital N, it must be less than this r here. It must stay within this bound here. Okay, for the limit to exist. So this is your limit here. It must be less than r. So this statement will always be true. Okay, so we continue from this statement in the next video.